Welcome back to ECE 320A. Homework number 2 is a little bit longer in length than homework 1, and you might want to get started. There is some material, or some of the first few problems are dealing with Chapter 10 material. The latter part is dealing with Chapter 11, and we'll try to get through as much Chapter 11 as we can today. The exam is a week from Thursday. It's coming up pretty quickly. There is some Exam 1 material on D2L. Apparently there might be some more if we have a review session, and I will try to see when we can schedule such a review session to happen this semester. Today what I want to do is cover all of Chapter 11. What I will try to do is get through this list, which is to continue with three-phase circuits. We will talk about the restrictions, and essentially it's plus is not equal to minus, or positive phase sequence and negative phase sequence. You do not want to try to interconnect systems that are operating in those different sequences. That's the interconnection restriction. We will then have a quiz related to balanced three-phase voltages. Then we will talk about the different possible connection types of either sources or loads, and I guess I'm doing a lot of hand signals. There's the delta connection and the Y connection, and then there are the 4 different possible ways that you can combine sources and loads. We will look at those schematically rather quickly. I've just already written those down, and I'll slide those by you. I don't know that you'll be able to copy those down as quickly as I want to get through those. But then we will start to look at how do we compute the complex power associated with three-phase systems, and we'll isolate on one particular phase, and luckily a single phase uses exactly the same formula that we've been using in Chapter 10, VI star. That gives us our complex power when V and I are phasors. If we have a balanced system, then we can just triple that, because each of the phases will have the same power associated with them. The A phase, B phase, and C phase will have exactly the same real and reactive pieces, and we can just multiply one phase by 3 to obtain the total complex power. One of the difficult parts of this is terminology. This meaning three-phase power. We will try to talk about phase voltage and phase current, but that depends on how the loads and the sources are interconnected. When I refer to the phase voltage, you need to know, is this load Y or delta connected, and that will determine what this means. I hope that will become a little bit more clear when we get to the diagrams and the schematics. We will then try to justify or explain how we can essentially extract from a three-phase balanced system just a single phase and analyze that single phase. And in so doing, we've captured all of the information that we need based on that three-phase system. It's important then to figure out, where does this single phase equivalent come from? At the end of last lecture, I think I made this comment or this statement about, if you have a positive phase sequence, do not connect that with a negative phase sequence. Mechanically, they're spinning in opposite directions, and you don't want to connect them. Electrically, we've been saying these phases are these counterclockwise rotational spinning phasors, and we are looking to see, oh, positive is ABC, negative is ACB. But this is just a schematic that I'm trying to emphasize with the red X. Don't be connecting things. And this is more for you when you get out and you're working with these systems. We probably won't be trying to trick you into saying, oh, here is a positive phase sequence and here's a negative phase sequence and they're interconnected. No, it's hard enough to just play with things that are okay to play together, positives with positives, but you can have loads, Y connected and delta connected, in parallel with each other. That's okay. It's just the sequence can't be different between the two loads or sources. Here's our quiz. Well, maybe even before we get to the quiz, can you remind me what a set of balanced three-phase voltages look like? And I've done the hard part. The magnitudes are the same. The lengths of all of your vectors are equal. What goes in the angle? If this is a positive phase sequence or an ABC sequence, how do I complete these two blank values? Plus in one and minus in the other. And what's the angle associated with those? 120. All right, here I have a confession to make. How many of you, since last week, see three-phase systems in your microwave? I opened up the door this morning and I saw the turntable and the supporting structure underneath that it spins on. Had 3 prongs and they were how far apart? 120 degrees, and I go, oh no. So I saw a balanced three-phase set of voltages in my microwave this morning. This one, which one is which? You said they're plus and minus. You said they were 120. That one is, they're both less than 180 is the reason why we could have one being minus 120 and the other one being minus 240. That's equivalent to a plus 120. Here's the quiz. What if we combine those? What if we add those 3 phasors together? What's the answer? And now you could do this graphically with your ruler and a straight edge and a protractor. You could graphically sketch these. You've now told me that this positive phase sequence, let's say that here is the A phase, here is the B phase, and there's the C phase. But if you combine those head to tail, so if we go from the tail of A to the head of A, we go there. Now if we include B, we go at the head of A, we now go down 120. And then we go in the direction of C, and I think that you see that this is equal to 0. Those 3 phasors, when added together, give us an answer that's 0. We get back to where we started by combining those phasors. Yes? The and. Oh, what does the N, not the and sign, the capital N, Nevada? Nevada? No, it doesn't. Sorry. I have to give you my thinking process here. We usually have subscripts. A lot of times they're M and N, and I may not enunciate clearly, so I call them Michigan and Nevada. But Nevada refers to the negative terminal. N is corresponding to neutral, or the neutral conductor in our system. That's what the capital N is referring to. So we're measuring from A to neutral, B to neutral. If you had 3 terminals coming out of this, let's say, machine, and it was a 3-phase system, you would have an A terminal, a B terminal, and a C terminal. And those are now, if it was Y connected, would be referred to, then let's say the A phase was the voltage between the A terminal and neutral, V sub Bn is B terminal and neutral, etc. So Nevada or N stands for the neutral conductor in this set of voltages. And here I was just using them a little bit more cavalierly. Here was V sub A, V sub B, and V sub C without a second reference point. Now, if this is true, so what we are saying then, in a balanced, and that's what we are calling these, a balanced three-phase set of voltages says that we have V sub A plus V sub B plus V sub C equaling 0. What if we took that just a little bit further and I said, what about the instantaneous? Can you create the instantaneous A phase voltage given the phasor form capital V sub A bar? What does the phasor give you? It gives you the magnitude and the angle. You would have to be told what the frequency is. And in this class, for the power, omega is 2 pi f, and f is 60. It's 377. We know omega. We know the magnitude. And if it's an RMS, you have to increase it by this square root of 2 factor. And we know the phase of each of those three instantaneous waveforms. Whoops, why did I give you the answer? V sub A plus V sub B plus V sub C is equal to 0. Do you see that connection? If the phasors give you 0, then for all time, if it's balanced, those three instantaneous voltages, if summed together, would give you 0. And we are going to use that a little bit later when we start deriving the single phase equivalent. Before we get there, let's talk about the different ways, and there are only two ways that we are talking about, 2 ways to wire three-phase voltage sources. In the Y configuration, there's the A phase. This is now V sub A. The B phase, and I'm trying to draw this so that you see where the Y might come from. Here's the B phase. And then we have the C phase. And you could see that these terminals could all be coming out of some machine, and internal to that machine are these voltage sources. This is the Y connection of our sources. What I'm not showing are impedances that are naturally going to be in there, and I'll fill you in on what those are, but I just didn't in this simplified diagram of a set of three-phase voltage sources in a Y connection. That's the Y. The delta looks like a delta, and here let me say that I'll call this the A phase. Let me call this the B phase. And this is the C phase. So that coming out of the positive terminal of each of these is the A terminal, the B terminal, and the C terminal. And I hope that it's clear that this looks like a delta configuration for interconnecting those sources. And again, I have not included these boxes, could include the generator impedances or the impedance internal to the source. So let me show you what those look like. The above sources were drawn without generator impedances, where the generator impedances are really just a bunch of wires, and we lump those into the winding resistance, R sub W, and the winding reactance. Meaning in each of those phases, so that blank could be A, B, or C, we have a Z sub G, and we're reserving the lowercase to be on the source side. This would be now the resistive winding plus J X sub W in either A, B, or C. And these Z sub G's are where I've indicated those blue boxes. If you wanted to have a more realistic voltage source, you would include these series resistance and reactance in each of those sources. A lot of times we just say, let's neglect those. And if we say neglect those, then we end up with this without the blue boxes or that without the blue boxes. But do you see that these could actually look the same in terms of the terminals, ABC versus ABC? Although here, we actually have the ability to maybe have access to the neutral. Sometimes we might actually have a neutral conductor in a Y-connected load. And that might then be available to us, and then we can actually measure between the A terminal and the neutral, the B terminal and the neutral, C terminal and the neutral. In the delta connected, all we can do is measure between terminal A and B, terminal B and C, and terminal C and A. Questions on the sources? Those are fairly straightforward. Now let's go into the loads. And now I will try to remember to capitalize all of my subscripts. Like the sources, these likewise can be Y or delta configured. In a load, let's say that now we have a Y-connected load. And here's the A terminal, the B terminal, and the C terminal of that Y-connected load. And we have our delta connected load. And not maybe to distinguish between these, this is not the same Z sub A necessarily. If you wanted these to look compatible or consistent between the terminals or equivalent, then this impedance would not be the same value as the impedance in the Y connected. So let me bar that just to let you know that that's not the same impedance value if we wanted to convert between a delta configuration and a Y configuration. And we do want to know how to go between Y and delta or delta and Y. If somebody gave you a delta connected load, you might say, oh, I would be much happier to analyze this if I could make an equivalent load that was Y connected. And that's what we are going to be doing. But those are the two possibilities for our loads. Now if we interconnect those, two source combinations and two load combinations, we end up with four possible arrangements. Just to be clear, we could have multiple source or multiple loads on our sources. We could have a Y configured source with a Y configured load. We could have a Y source with a delta configured load. We could have a delta source with a Y load, or we could have a delta source with a delta load. And those are our four possibilities. And what we are going to be focusing on in this class probably is it's easier to analyze everything if we can do just a single phase equivalent. If somebody gives us maybe a delta Y, maybe we want to convert the sources into a Y, and now we have a YY. Now we can extract a single phase equivalent, and we can do the analysis on that single phase equivalent. Let's look at what these look like. Wow, is that busy enough? I can make it even busier, but this is now the YY configuration. Like I said, don't try to copy this down. I will make this available to you, but do you see the Y and the Y? Here is the Y of the source, and here is the Y of the load. And these are all labeled, hopefully somewhat consistently. This voltage source on the left for the A phase is A prime, that terminal between the source and the generator internal impedance is the A prime node. If we had a non-zero capital Z sub GA, then the voltage at A is a little different than the voltage at A prime. Our transmission line impedances are with lowercase l's, and the loads, we may just give those uppercase subscripts. In this diagram, is it clear what I'm meaning by the voltage across the A phase load? If you took a voltmeter and connected it up to measure the voltage dropped across the A phase in the load, where would you attach those leads? You would put one in Nevada and one in Arizona. The A phase, right? And who won? Well, never mind. Just saying, right? We have to be on current events. Okay? A and N. Is it clear that we would be going between here and there to measure that voltage? That's the A phase voltage. That's not the same as the line voltage in the A phase. That's why I said this terminology can be a little bit particular. I could now measure, if I didn't have access to that neutral conductor, maybe I couldn't even measure that A phase voltage. Maybe all I could measure are the terminals between A and B, and that's called a line voltage or a line-to-line voltage. The line-to-line voltage would be from A to B. And that's not the same as the phase voltage in that interconnection or in that Y configuration. Do you see the difference? The line voltage involves two phase voltages, the A phase and the B phase, and a particular combination of those. We will show how to relate those quantities to each other. But now I just want to make sure that we're clear on the distinction between line-to-line voltage, which a lot of times is just stated as line voltage. That's the voltage between A and B, or between B and C, or between C and A. Those are all line-to-line voltages. Phase voltages are V sub A in, V sub B in, and V sub C in. The currents here, I sub little a, capital A, that's the A phase load current. That current goes through the A phase load. And that's also the line current in this Y connected load. The phase current and the line current are the same. Our phase voltage and line voltage were not the same. That's the Y. A Y delta. They're going to think we're having a, never mind, some kind of convention. We're going Y's and deltas. We don't have any gammas here or lambdas, not today. So it's just Y and delta. But now our load is in a delta configuration. Now if I wanted to know the phase voltage, that's the voltage dropped across the A phase in the load, and what is that? That's between A and B. That's the line-to-line voltage. Do you see now in this configuration, in the delta configuration, the line-to-line voltage or the line voltage is equivalent to the phase voltage? You just said it wasn't. Well, I said it wasn't back here, way back here in the Y. There's this distinction. Now, what about the line current? Is that the same as the phase current at the load? No. Do you see the difference? I sub little a, capital A is not the same as I sub capital A, capital B. In the delta configuration of the load, the phase current and the line current are different. The phase voltage and the line voltage are the same. We had just the opposite in the Y-connected load. There, our phase voltage was not the same as our line voltage, but the line current was the same as our phase current. Yes? Okay, so you said that for the Y line voltage was combination of phase voltages. Yes. So for the Y delta is the line current. Now to relate these line currents, what you could do is apply one of your favorites. You could do KCL at one of those nodes. And now you could see, well, maybe it's, well, it doesn't matter. Now you can see that this guy I sub little a, capital A is made up of I sub capital A, capital B, and I sub capital C, capital A. by KCL. And we will derive those relationships for balanced voltages and currents. And now we will start to see these angles of 30 degrees and these square root of 3s coming into this relationship. But that's forthcoming. Here's the delta to Y. What's the same? Phase voltage, line voltage, phase current, line current at the load. I have to make that distinction. At the source, it's different because now we're connecting deltas with a Y. Let's concentrate at the load side. What's the same? The line current is the same current going through each of those phases. The line current and the phase current are the same in the Y connect to the load. The phase voltage is not the same as the line voltage.
When you say phase current, are you referring to the load?
So there you have, the question is a good question. It really needs to be clarified in terms of what I was specifying. The question was, when I said line current, am I referring to the load or at the source? I really need to tell you. So it's not really clear, but I said, let's just worry about the load. And if that's the case, then I'm saying, what is the line current? The line current is really what's the current on the transmission line between little a and capital A. That's the line current. That's always the line current. But in the load, is it the same as the phase current? And in this case, in the load configuration of Y, it is. But if we went back to the source, then our phase currents at the source are not equal to the line current. Question? So the phase current runs between little a, in this case, yes, in the Y-connected load, the phase current is flowing through the A phase of the load. It's flowing through capital Z sub A. It's now going from capital A to capital Nevada. Other questions on that? And here is the delta-delta configuration. You still have all of the pieces and the parts, but now you have the load connected in delta and the source connected in delta. And now your currents, or the line currents, are definitely not phase currents in either the load or the source. The load voltage or the line voltage is the same as the phase voltage in this configuration at the load. Other questions? Now,
Is there a reason we're always analyzing the phase voltage and current at the load as opposed to the source?
the question was, why are we focusing on the load? The answer is we could focus on either one, but a lot of times we're maybe more interested in what's happening at the load, but we're interested in what's happening at both. But if you understand something at the load, you apply the same techniques at the source. So if I ask you for what's the complex power supplied by the A phase source, you should be able to figure that out from the diagram and the configuration. If I say, what's the complex power in the A phase of the load, likewise you can do that with the appropriate current and voltage. Let's do that. I have so many pages here, I don't know where I'm at. Here is then, what configuration is this? I'll cover it up. Did that help? I'll cover it up. Workers' comp. Any more questions? All right, so now we have our YY configuration. I want you to find or tell me, how do I find the complex power in the A phase of the load? What expression or variables would you combine in order to, and I'm assuming all of these variables are in RMS units. What equation would you use to find capital S sub A bar? Did everyone get that? I'm sure everyone picked it up on the microphone. No? Yes? It's our standby formula, right? It's VI star. What we have to figure out is what's V and what's I. I want the A phase. So now I need to know the phase voltage in the A load, and I need to know the phase current in the load at A. The A phase voltage, I hope you see that that's the voltage dropped across the A phase impedance, which is simply V sub capital A capital N. Again, I'm assuming all of these are in RMS. And now I need to multiply that by the conjugate, complex conjugate of the current going through the A phase. And that's just capital I sub little a, capital A. And it's a passive sign convention. I don't have to worry about changing the sign. This is now, if we wanted to think about it, this is the phase current. Which is equal to the current through Z sub A. And it's actually equal to the line current since our load is Y connected. This is our phase voltage. And what do we know about that relative to the line voltage? And when I say line voltage, that's usually meaning line, transmission line to transmission line. And this would be at the terminals of the load, wouldn't it? So in this case, I hope it's clear that the green V sub AN is not the same as the capital red V sub AB. The line voltage in the A phase is not the same as the phase voltage in this Y configuration of the load. So in this particular Y connected load, V sub AB is definitely not V sub AN. This is the line-to-line voltage, and a lot of times we will just abbreviate that to the line voltage. And this V sub AN is our phase voltage. In our Y-connected load. Are you okay with the expression for the complex power in the A phase? Yes.
This is line-to-line voltage for the A phase.
This is the line-to-line voltage of the A phase. So we're saying that we're going from the A terminal, the positive terminal of the A, to the B terminal. So the B phase would be from capital B to capital C, positive to negative. What would be the C phase voltage? I'm sorry, the C line voltage. It would be capital C all the way up to capital A, positive to negative. So you would connect your voltmeter, the negative end to capital A and the positive end to capital C, and that would be your C phase line voltage. Do you see how confusing this can be? C phase, but it's the line voltage, and I was talking about phase voltages at another point. So you really have to be clear what it is that we're referring to. But I hope that it's okay for you to believe that the complex power in the A phase is the voltage dropped across that A phase load times the complex conjugate of the current going through that load, which is V sub AN I sub AA star. If we wanted the total power, then if this is a balanced system, to obtain the total load power, that's now S sub A plus S sub B plus S sub C, but if it's balanced, each of those is exactly the same, and so now we have 3 S sub A, or we may just say 3 S sub phase. And that's the total load power, all 3 phases combined. Questions on that? Yes? These are definitely at the same frequency. These are all basically interconnected. They are just 120 degrees out of phase, but they're all spinning at omega, these voltages and currents. It's interconnected. They have to play nice together. And they play even nicer if they're balanced. Questions on the YY configuration? What if we changed it up a little bit, and now I said, well, what about the Y delta configuration? Here, let me try to sketch this. Let's say that we have Z, and here I will be even more maybe specific. Here's the A terminal at the load. And now I have, is it okay if I do that? That's the same point. I'm just stretching my line. No impedance loss there. And here's C, the same C. But now if I expanded on back, my source would be a Y connection. I'm not going to take the time to do that. But here is my line current in the A phase. Here is my line current in the B phase. What's my phase voltage in this configuration in the A phase? What's the phase voltage in the A phase at the load? That's V sub A, capital B, isn't it? Meaning now we would have that voltage drop from terminal capital A and terminal capital B. if you had to compute the power, the complex power in the A phase of the load, could you do it with the information given so far? What do you need? You need the current through that A phase load, don't you? You need the current flowing from capital A to capital B. If you had that, then you could find or compute the complex power of the A phase in the load. Let's do that. Let's just write the equation. Here is now the A phase load power as a formula. That's now V sub AB, that's the line-to-line voltage, times I sub AB conjugate. And again, this is in a delta load configuration. This is the phase voltage. But it's also the line voltage. What about this one? That's the phase current. Is it the line current? It's definitely not the line current. In this case, I sub AB is not equal to I sub AA. What's the total load power? If we, well, if you didn't know anything else, you would say, well, give me the A, give me the B, and give me the C. And it could be unbalanced, and that formula would still work. Give me the complex power in the A phase, give me the complex power in the B phase, give me the complex power in the C phase. I'll add those up, and that's the total load power. If we are working, or if our system is balanced, then all of those different phases in the load are equal, and we could just look at the A phase, or we might just abbreviate that or change that and say, oh, our per phase complex power is capital S sub phi, and we just triple that to find our total complex power. Questions on that? Now, to get you started with some of these problems, if you were trying to do delta to Y or Y to delta conversions, did you do that in 220? So you know where those are at in the book? What was that? Psst. That's not allowed. No, it's allowed now. But if we were doing impedances, I've tried to find those. And if you look on page 324, section 9.6, that's for complex impedances. And if you wanted to go back and say, well, let me just see what that looks like when I have completely real impedances or just resistors, that's in section 7 of chapter 3 on page 71. And in particular, if you wanted to go delta to Y, then you are going back to equations 51 through 53 in chapter 9. If you wanted to take a delta configuration of impedances and convert those to a delta, those are the next three formulas, which are 54 to 56. And if you had sources, the impedances of sources, you would do the same way. If you had Z sub GA, Z sub GC, and Z sub GB in a delta, and you wanted to convert those to a Y, you would use these same formulas, those impedances. And we'll learn how to convert the voltages from deltas to Ys in a little bit. Let's now talk about analyzing these circuits. In analyzing, the notation is critical, but I think we've already sort of established that. We are using a double subscripted notation. Where if I say V sub AB, then it's the voltage dropped, or the voltage drop from the first subscript to the second subscript. With that notation, let's now see if we can derive or verify or justify how we can extract a single phase equivalent from a three-phase circuit. And the reason we're doing this is so that we can now go back to chapter 10 and do all of our analysis using the techniques that I hope you're already comfortable with. It's just now we have to learn how to extract that information from the three-phase system. This is now going to be talking about the three-phase to single-phase equivalent justification. And we will do this for a YY circuit, which really means if you had a Y delta, then convert your deltas into Ys, and now you have a YY circuit, three-phase. Now we can extract the single-phase equivalent from that circuit. If we go back to our YY configuration, what I want to do is first try to find the current that's flowing in the neutral conductor. To get us started, to wake you back up, let's do a quiz. I want you to write a KCL equation at node little n. And now I have to go find little n. There. There is a YY system. I'm now using little n as my reference. I want you to write a KCL equation at little n. This is your interview question. Do you have any tissues? My brow's getting a little sweaty. Okay, just step back and take a deep breath and say, okay, let me just write it in terms of the currents, I, not in terms of voltages and impedances, but can I now write KCL in terms of the green I's, the line currents, and the blue current I sub 0 in the neutral conductor? Can you write KCL there? And don't say, right? You can write that one, I hope. What do you know about KCL? The currents algebraically sum to 0, or the sum of all the currents entering a node are 0, or the sum of the currents leaving a node are 0. How many currents, as I've sketched that, are entering little n? 1, and it is I sub 0. What's leaving? The 3 line currents. We've written KCL. That was easy. Let's then follow that along. So now this KCL equation at little n is now I sub 0, those are the ones coming in, equal the ones going out. Voila. Right? For this crazy circuit, that equation is valid. Now, if little n is my reference node, what's the current I sub 0 in terms of voltages and impedances? Yes. I sub 0 is the sum of the other currents, but now I want to change that a little bit. Let me try to express I sub 0 in terms, and I don't even have it on here, do I? What's the voltage across that impedance? It's capital V sub capital N sub little n, and little n we're saying is our reference. So can I just call that capital V sub capital N? Is it clear what that reference is, or what that voltage is? That's the voltage from here to there. So this is V sub N. Yes. Yes, so that's V sub capital N to little n, and little n is my reference, so I'm going to say that's like 0. That's my reference node. So we define capital N as neutral. That's correct. And now if these two neutrals are not at the same potential, we've got current flowing. That's the idea, right? So now what we don't know yet is, do we have current flowing through that neutral conductor? That's what we're trying to express in terms of some variables. We now are saying that is it clear what I sub 0 is equal to in terms of these newly defined variables or quantities? It's capital V sub N, which now if you had a voltmeter, you would put the positive lead at capital N and the negative lead at little n. That's now measuring capital V sub capital N. We divide that by Z sub 0, and that gives us I sub 0 flowing from right to left in the positive direction. So I sub 0 is now V sub N over Z sub 0. Now you can see what we have to do. We have to find I sub little a capital A. And what is that? capital I sub little a, capital A is flowing through three different impedances in the A phase, and the voltage across that is just the voltage from the A prime terminal over to the capital N terminal, that difference. Do you see that? The voltage dropped across those three impedances is V sub A prime little n minus V sub n, and what the impedances equal, we had our generator impedance, we had our transmission line impedance, and we had our A-phase impedance. Consistent with that, we could have all of the other. You know what? I'm going to call that Z sub phi in a minute, and I'm getting lazy. This I'm going to call Z sub phi because I'm going to assume they're all equal in a minute. Is that okay? But you could make this a little bit cleaner by saying that this is, and now I'm doing it, Z sub GB plus Z sub LB plus Z sub B, etc. for the C phase. Does that now re-express that KCL formula? Yes.
You want to go from, you want to say n minus prime, and that's
So now I need to make my current I sub AA positive going from left to right. So now if I sub AA is going from left to right, I need, in fact, A prime to be at a higher potential than capital N. So I need to subtract capital V sub N from V sub A prime N. Is that okay? The way that I've labeled that, hopefully it's consistent, and now I want to go from what's my voltage from A prime to capital N. And that I represented as V sub A prime N minus V sub N. If all of this is balanced, here are some conditions that are associated with a balanced three-phase circuit. One is we have all of our source voltages form a set of balanced three-phase voltages. VA prime N, VB prime N, VC prime N form a set of balanced three-phase voltages. And if I shouldn't say this because somebody might take it out of context, but stick your head in a microwave and you know what those voltages are, right? They have the same magnitude and they're separated by 120 degrees. Don't do that, please. But you can observe. Another condition for a three-phase circuit to be balanced is for all of these generator impedances to be the same. We also want the transmission line impedances to be the same. And we need our load impedances in each phase to be the same. If that's the case, then I can make the following claim. I can state the following fact. If the system is balanced, then that neutral, or the voltage at that capital N terminal measured relative to the little n terminal is 0. There's no voltage drop across that neutral conductor. If we were in a math class, that fact would be a theorem and we'd have to prove it. That's why I said it's a fact. But now I'm going to turn it around and prove it. So now we're in a engineering class and we have to prove that fact. So I didn't want to get you too sweaty from nerves with a theorem, so I just called it a fact, but now we're going to do a proof. And to start, let me just go back to what I said I was going to do. This z sub phi was going to be z sub a plus z sub la plus z sub ga. And then, with that, I can rewrite this equation. I'm trying to show that capital V sub capital N is equal to 0. Let me pull all of those V sub N's to the left-hand side. I have a Z naught, and then I have a bunch of Z sub phis on the left-hand side, scaling capital V sub N. I now have V sub N scaled by 1 over Z sub 0 plus, since I'm moving all of those on the right had negative signs, I'm moving those to the left. I had 3 of those. And what's left on the right? Everything on the right is over exactly the same denominator, isn't it? Those denominators are all Z sub phis. So I have V sub A prime N over Z sub phi, I have V sub B prime N over Z sub phi, and I have V sub C prime over Z sub phi. And those are just added up. And now do you remember our quiz answer from before? What's the sum of a set of balanced three-phase voltages? Remember how we connected those tail to tail and formed a nice equilateral triangle? Do you see the triangle? Just doing this for the people out waiting for the class after us. They're going, man, they have fun in there. Hypotenuse, do you see the hypotenuse? Do you see the horizontal line? Do you see the equilateral triangle? If you do, then you see that. It's 0. So this is now 0 Z sub phi, and we know that this is a combination of positive values. That's not equal to 0. We can now solve for V sub N, and boy, that was one of the cleanest proofs you'll ever find, huh? QED, or just square that's filled in. What does that mean? This is a big star. I wish I had a gold pen. I'd put a gold star, but I'll settle for a blue. You seen any blue stars lately? There's one on the board. There is no voltage drop. This is now saying there's no voltage drop between the source neutral, that was the little n, and the load neutral, which was capital N. So now we know there's no voltage drop across that neutral conductor. If there's no voltage dropped across that neutral conductor or that impedance of Z sub 0, how much current is flowing? No current is flowing in that neutral conductor. What are we assuming is true for that to be the case? It's balanced. We had a balanced three-phase system. With these two stars, it gives us two options in terms of what we can do now. If we don't have any current flowing through that neutral conductor, why don't we just pull it out of the circuit? There's nothing flowing in it. Let's just remove it. So that's one thing that we could do. That's one option. Remove the neutral conductor, since I sub 0 bar is equal to 0. That's with a balanced system, and we have what? This sum of I sub AA, I sub BB, and I sub CC all flowing through that conductor. And since it's balanced, they all sum to 0. In a real system, that might be why the neutral is there. If something becomes unbalanced, then we have somewhere for that current to flow. The other option, if there's no current through that, why do we need to worry about the impedance in that? Why don't we just replace it with a short circuit between little n and capital N? So that's our second option. Replace the neutral conductor with a perfect short circuit. And that's now using the fact that that voltage was 0. Now, now that we know all of that, can we say anything about the currents in that circuit? What is I sub A? What is I sub little a big A? That was V sub A prime N minus V sub N over Z sub phi. We just said that V sub N was 0, so this is now V sub A prime N over Z sub phi. What's I sub B B? Same structure, just a different phase, isn't it? It's now V sub B prime N over Z sub phi. And what is I sub little c big C? Same structure, it's now C prime N Z sub phi. What can you now say about those currents and how they are related? What is Z sub phi? That's all of our impedances, and what does that look like? That's just a complex number. Has a magnitude and an angle. And we are now adjusting all of these balanced three-phase voltages by the same complex number, same magnitude and angle. What's that going to do to our eyes? They will be offset by whatever Z sub phi is, right? But they'll all be offset the same. And we started with these V's looking like balanced three-phase voltages. If we just all offset those by the same magnitude and angle, the currents will be a balanced set of currents. Is that clear? They'll have the same magnitude and they'll be offset in frequency by the same 120 degrees, which means then that our current in each line is equal in magnitude or amplitude and obviously in frequency, and are 120 degrees out of phase with each other. Which now says that we are ready to extract a single phase equivalent circuit. We can now just look at the A phase and analyze that, and that's where we will pick up on Thursday.